Chapter 9, Correlation. This is one of my favorites. So one of the things that I love about my job is that statistics is not like any other subject, like physics, chemistry, biology, psychology, teaching, in that I don't study statistics just for the sole purpose of learning about statistics. I study statistics so that I can help solve problems in all other disciplines. So I get to play with everybody else's data. That's why I love what I do so much. So we're going to start with a motivating example. So Dr. Mortimer is interested in knowing whether people who have a positive view of themselves in one aspect of their life tend to have a positive view of themselves in another aspect of their lives. So he collects 80 men to be in his study and has them fill out a 5-scale questionnaire. 4 of the questionnaire scales have to do with different areas of their life: intimacy and relationship with friends, common sense reasoning, everyday knowledge, and academic reasoning and scholarly knowledge. So how they feel that they do, or how competent they are in each of these 4 different areas. And then there's a 5th scale that says how competent they feel, their self-concept of themselves overall. So we've got 5 measurements about confidence. Each person has the view of themselves. So each person has these 5 measurements. This is where correlation and regression, these next 2 chapters, are different than all the other ones we've done up to now. Starting now, we're talking about situations where we have multiple measurements per person. In this case, we have 4 subscores and kind of like an overall area, but we have 5 different measurement values for each person. So of those 5 different measurements, we can pair them up. So the first with the second, the first with the third, the second with the 5th. If you have 5 scales, there's 10 different ways you can choose 2 of them. And so there's 10 pairs of those 5 different measurements. And we can calculate a correlation for each pair. Specifically, I want to stress, correlation is a pairwise or a bivariate relationship. So when we did in like chapter 3 and 4, when we were talking about summary statistics and distributions, we were talking about one variable at a time. A variable's mean and standard deviation. Now when we're talking about correlation, is the relationship between a pair of variables, between 2 variables. Now in this case, we have 5 variables, so there's 10 pairs of variables we can study when we're looking 2 at a time. So correlation specifically is when we have continuous variables and we want to know what's the degree to which they covary or correlate with each other. So we're not interested in if 2 groups are different. We want to know if they correlate or covary with each other, 2 different measurements. So if we're looking at variables that have order to them, their ordinal or interval ratio, we call it correlation. If we're looking at variables that don't have order, so nominal variables, so that'd be like race and ethnicity and country of origin, those would be nominal variables. And if we want to know about a connection between 2 nominal variables, we just call it association or dependence. The word correlation is reserved for when we're talking about ordinal or continuous variables specifically. So we want to know to what degree do these 2 variables kind of move or hang out together, or some of the terminologies that are used. We can talk about this in terms of raw or standardized formats of the variables. Really fun concept with correlation is it's scale independent, scale invariant. So it doesn't matter if we measured temperature in degrees or Fahrenheit. It doesn't matter if we measured height in feet or inches. It doesn't matter if we measured depression with a Beck inventory or a DSM-4 criterion scale. As long as we have a scale, the units aren't so important when we're looking at covariance or correlation specifically between 2 variables. Now, when we calculate the correlation is an interesting statistic because it is a statistic in that it refers to the sample, but it is also a measure of effect size at the same time. But we can do hypothesis testing on correlation, just like we've done correlation or hypothesis testing on mean differences and hypothesis tests on a single mean. So, like all hypothesis tests, the null hypothesis is nothing's going on. So if we're looking at two variables at a time, the null hypothesis is that there's no connection, there's no association, there's zero correlation. So the null hypothesis is zero correlation. So, common thread through all the chapters, always plot your data first. And this is why R is such a favorite of my tools, is because it makes plotting relatively easy. So here we have a plot, and we're going to look at this code more in a minute, but we want to make a scatter diagram. And a scatter diagram is a plot that we can do two variables at once. So far we've looked at histograms and bar plots, but histograms specifically and box plots, that's when we have one variable, the distribution of a variable. And we can look at its center and spread, its mean, standard deviation, its median, its interquartile range. But now we're looking at two variables at a time. So we have to choose one variable to be the x-axis and the other variable to be the y-axis. Now, obviously, if you have two variables, you have two ways you could put the variables. You could put the first variable on the x-axis and the second variable on the y-axis. Or you could have done it the other way around. For correlation, it doesn't matter which one is on the x-axis and which one's on the y-axis, but we want to make it so that each pair of measurements, each person usually, is a point. So we're going to go on the x-axis, the value of whatever that x variable is, and the y-axis, whatever that variable number is, and find where they connect, and that dot is the observation or person. So scatter plots can give us a lot of information visually before we start crunching any numbers. We can also make paneled plots with the facet command to do them by subgroup. But the key is 1 point per person. And then we can overlay a line. And this is kind of like looking ahead to the next chapter, chapter 10. The regression line is the line of best fit. So that will be chapter 10. But right now, chapter 9, we're looking at the correlation. So when you look at a scatter plot, you want to take your eyes and kind of squint them a little bit and look and see, is there a general pattern to this cloud of points? Because statistics is not concerned with individuals, but trends, relationships. We don't care about Johnny or Sue per se. We want to know what's the relationship between variables, between depression and anxiety, between height and weight. That's a really kind of less exciting example. But we want to see relationships between variables generalizing over all people in our population we're concerned with. So when we talk about correlation, we can talk about several different aspects: direction, strength, and form. So direction, we can either have a positive or a negative direction. And this goes along with the positive and negative slope you learned about in plotting way back in middle school and high school. So when we're reading from left to right, if the line is going up, it's a positive relationship. Positive relationships are when the two variables, high goes with high, low goes with low. So I think an example that is often given is hours spent studying and grade on the exam. Now, it's not a perfect relationship, but generally people who study more get higher grades, people who study less get lower grades. Now, there are exceptions to every rule. Some people just get it without studying. Other people study forever and just freeze up on the exam. But generally, there's a relationship where high on the study time goes with high on the exam score. Low study time partners with low on the exam score. So when they're both high together or both low together, that's called a positive relationship. A negative relationship is the reverse. So this would be time spent on video games and score on exam. Here we go. The more we study on the more time spent on the video games, I'm talking about my kids, the lower their score, and vice versa. So as you read from left to right, it's going to be going down, and that's what we call a negative association. So correlation has direction. It also has strength. The strength of the relationship is visually pictured as how tight the points are around an imaginary line of best fit. So in this first plot, we have a very strong relationship. In fact, it's pretty much as strong as you can get. We have a perfect line. So this would be a very strong positive relationship. You can also think about it if we had strips in the plot. If you knew what X was for a given person, you would be able to perfectly guess their Y value because there's no movement in any little strip on the plot. It's all concentrated. To compare that, here we have a weak relationship. It's still positive, is going up, high on the x-axis variable partners with high on the y-axis variable, but there's more spread, there's a more diffuse cloud of points around what would be our imaginary squint and see it regression line or line of best fit. So if you take any kind of strip of the plot above an x value, you're going to have more variation. You're going to have a little bit more wiggle room for what the y-axis value would be for any given point on x. So strength is how tight the points are to the line. Direction is whether it's going up or down. So here I have two different scatter plots. Now both of these have roughly the same strength. I mean, you squint your lines, you can kind of see about the same size pattern. The difference is the top one we would call a linear pattern because it's going in a line-ish shape, versus the plot on the bottom we call a curvilinear or a non-linear pattern because it has kind of this U-shaped bend. Now, it's still a relationship. I just want to stress it's not a linear relationship. So we could look at this as like how well people or time spent running the mile. So really, really young kids take a long time, like elementary school, to run the mile. Then as people age, they usually get better, and then at some point they get worse. There's a lot of things in life that have curvilinear relationships. And again, I'm stressing it's not bad, it's just not linear. These last two plots I'm throwing up, both of these are two different situations that have what we would call no relationship or a zero correlation. So the right top plot has no relationship. When you squint with your eyes, you can't even tell if it's going positive up or negative down. It's kind of just diffuse everywhere, kind of flat and even. That's a no relationship or a correlation of 0. The bottom right-hand corner, this last plot of no relationship, sometimes will trick people. And this is where we have a perfect line, but it's perfectly flat. This is also no relationship because knowing the x value gives you no information about the y value. Now, in the reading and on another slide, we're going to talk about restricted range. So sometimes this happens if we have ceiling and floor effects. So you choose a measurement tool that you're going to use in your study. Say I'm going to use self-efficacy measures. Everyone in my study in a certain sample gets about the exact same score. There's no variation. When there's no variation on your outcome, then your predictor doesn't help you predict. And so this is something that we have to worry about when we're choosing our scales, our measurement tools to use in a study. We need to make sure our tool to measure fits our population, that we're going to get the variance. Not just that the scale can go from 0 to 50, but then in our population, we're going to see a good range because you cannot model no variation. If there's no variation, you can't model anything. Okay, so predictability, how well X would help you predict Y, is a good question to ask in determining the strength of a relationship. So again, here is that perfect +1, perfect straight line sloping up plot. If I know what the X value is, I can go straight up from that X value and perfectly predict Y. This is a perfect, strong, positive relationship. But again, if you have a more diffuse pattern, even if you can tell it's going up, knowing your X value for a particular person gives you a range of Y values. And if that range of Y values is not distinct as you move across your plot, because it's really fuzzy cloud of points, then it's a weaker relationship because knowing X doesn't give you as much information to predict Y, or vice versa. Okay, so here are 4 different scatter plots. I'm going to give you a second. I want you to look at all 4 of these and choose which one has the strongest correlation. Which one has the strongest correlation? Here's a surprise. All of these plots are the identical same data set. all of them. They're just stretched. If you look really closely at the X and Y axis units, they're just stretched differently. This top left-hand plot is zoomed out, so all the points look like they're close together, but there's very little range or variability here. If you look carefully, you can see how the plot below it has just zoomed in. The right-hand plots have zoomed in only one direction, so only zooming in on the Y direction or only zooming in on the X direction. When you plot data, you don't want to have wasted space in either the X or the Y direction when you plot, or else you can make it hard to see the degree of correlation. The good news is when we use R, it will automatically restrict the X and Y axes on your plot down to just the zone that your data actually would fill. Another problem with scatter plots, correlation and regression. We already saw in the mean and standard deviation that the mean and standard deviation are very highly susceptible to influence by extreme outliers or extreme values, that they have a lot of leverage of pulling the mean to the extreme high value or low value that's in the data set. Skewed distributions, the mean and median, are pulled away from the peak mode. Two variable bivariate relationships can have the same problem. Now, I have two plots here. Both of these have an extreme point, and I don't want you to get hung up on extreme point versus outlier versus leverage vocabulary. But on the left-hand side, we can see we have an extreme point that's in the upper right-hand corner, and the second plot has it in the upper left-hand corner. And I want you, we're going to use a little applet to see how this will influence the strength of the relationship in a couple slides. So we need a measurement like mean and standard deviation to be able to capture the strength and direction of a linear relationship. So this is the Pearson product moment correlation coefficient. That's the full name because Pearson was the person who published this. Product moment, we'll get to in a second, that's part of the equation. Correlation coefficient, a coefficient is just a value. And we're going to use the little r letter to represent correlation when we're calculating it on the sample. If we're referring to the correlation in the whole generalized population, we're going to use a Greek letter, and the Greek letter that has been chosen is called rho, R-H-O. Rho sounds like R, and it looks like a P when you draw it. It's a P without the straight up and down top and bottom. Now, rho, or R, the Pearson product moment correlation, is often just called correlation for short. Most of the time when people say correlation, they're saying that slang for Pearson product moment correlation coefficient R. And it's going to tell us the strength and direction of a straight line linear relationship. And this is often used to measure the correlation between an initial test and a retest, or person 1 and person 2, between alternate forms of a test or measurement scale to look at validity, agreement. It's a building block for a lot of other statistical models. So the direction is shown by the positive or negative sign in front of the R value. So R is a number that we calculate on sample data, and it does not matter when we calculate it which variable is X and which variable is Y. It is, the two are interchangeable in the calculation of correlation. We'll see it in the formula. It's also unitless. This makes it so it doesn't matter if we've measured in feet and inches, or if we measured in degrees or centigrade or Fahrenheit. Units are units. It doesn't matter. The range is between 0 or 1 in the positive or negative direction. So the sign, positive or negative, tells us the direction increasing or decreasing. The strength is by how close, weak is close to 0, strong is close to perfectly positive 1 and perfectly negative 1. But even though it has all these bonuses, it's unitless, doesn't matter which variable you're calling X or Y. It's always going to be between -1 and +1. Centered 0 means no correlation. It has all these great things about correlation. The negatives or the drawbacks of correlation this Pearson correlation coefficient, is that it only captures linear relationships and outliers can have a big influence. So I told you, here's the formula. You do not need to worry about memorizing this. We will not be doing this by hand, but I do want to peek at it before we get worried. So let's look inside these parentheses and see if this looks familiar. In the first parentheses, we have xi, that's each x value, indexed I, subtract the mean, divide by the standard deviation. Basically, that's finding the z-score of the x scores. We're going to standardize or find the z-score for the x values and the z-scores for the y variable. This is what gets rid of our unit by subtracting the mean and dividing by the standard deviation. We've standardized both of our variables. We threw out the units. And this is where the product moment part comes in. We're going to take the z-scores of the x values and the z-scores of the y variables, and we're going to multiply them together. That's our product. We add them up and divide by not n minus 1 to make it unbiased. It's the degrees of freedom thing. Yeah. So you can see there's not a hard math here. It's adding, subtracting, dividing. Not too tough, but there's a lot of little steps. So we do not want to do this by hand. We're going to let R do it for us. So this is how we do it in R. Just quick. We'll do a more in-depth example in a second. So here we have the code to do what we call a correlation matrix. Now in this example, I only have two variables. I'm going to call them var x and var y, whatever your names of your variables are. So you start with your name of your data set. You pipe it into the furniture package. Now we've done table F for frequency table, table 1 for descriptive tables. Now this is table C for correlations. And here we get the correlation matrix. Now with two variables, it's a 2x2 matrix. And you're going to have only the bottom half. The top half is going to be empty and one's on the diagonal. So there's only one cell in here in this little 2x2 table we need to worry about. And this gives the correlation and then in parentheses the p-value. Now this correlation matrix is better to use when you have multiple variables. If you only have two variables, you can test the correlation between the two variables with some code called core.test. Look familiar? We've done t.test. This is core.test. Now, the first thing we need to give is a formula. Now, we've seen some formulas before, and we've usually had a variable name with the tilde wave in the middle and then another variable name. For correlation, our two variable names show up on the same side of the tilde wave because x and y, it doesn't matter which variable is which. So the order of your variables does not matter, and we want them on the same side as the tilde wave. So we're going to do core.test, and the formula is going to be nothing, tilde wave, and then our variable names added together. And just like the t.test, we are going to tell it the data that's coming from above, and the default is to do the Pearson product moment correlation, but you can specify it as well. So the output will tell you it's the Pearson product moment correlation coefficient. And the correlation is actually the last thing that's listed on the bottom. So correlation being 0.054. Hey, that's the number that we got when we did the correlation matrix. So this is close to 0. 0 means no association, no relationship. So this is very close to a 0 correlation. Now we'll see in a second, the book teaches you how to do the table in the back, but we're not going to worry about that. It also converts the correlation to a t-score and can provide a p-value. This p-value tests the hypothesis that nothing's going on, there's no correlation. So we cannot reject that. It's when p is low, the null must go. But this p is big, a lot bigger than 0.05. So we keep the null hypothesis and we say nothing's going on, there is no correlation. The estimated correlation is 0.05, but it's not significantly different than 0. So there's a quick refresher or quick rundown of how to do correlations in R, either as a matrix or a specific test. And again, here's the p-value. And on the matrix, the p-value is in the parentheses. And these, usually the correlation and the p-value are the two things that are reported. So stressing, correlation only measures linear relationships. It tells you strength and direction, but only of a linear line relationship. So this would be a picture of a linear. This is nonlinear. If you were to calculate correlation R, this first plot, the linear relationship, that correlation might be a 0.5, 0.6. I'm just guessing here. eyeballs are not very good at guessing correlations, but I'm going to say it's 0.6-ish range. If I was to calculate correlation R on the second nonlinear plot, my guess is the correlation is going to be close to 0. There is not a very strong linear relationship, but we do have a strong nonlinear relationship. And there's nothing in the math, the calculation of R, if you were going to do it with the correlation, that would tell you it's nonlinear. The only way you know a relationship is nonlinear is to plot your data. So always plot your data. Okay. So we're going to go into this correlation app, and we're going to look at influences of outliers, eyeballing, correlation, drawing a line of best fit, all these great things. Okay, so I've been using this applet, this interaction, for many, many years. It's one of my favorites. Okay. So here we go. We can use our mouse, and this is really great because we don't have to use any numbers. We don't have to do any calculations here. I'm going to add some data points. So here are 2 points. And it's telling me, haha, you have 2 points, perfect correlation. Because if you have 2 points, you can draw exactly a straight line through. So anytime you have 2 observations, you have perfect correlation. Okay. Now I'm going to add some more points. Okay, these points are very close to a line, and you can see the correlation is 0.87, pretty high. Now, let's see, clear this. I'm going to put some more points. Again, we have a correlation here, but now it's a negative relationship. Okay, I'm going to clear this off. Now I'm going to do a whole bunch of points here. Let's get our good size sample. Okay. So we can see we have a positive relationship, and it's moderately strong. Strong, medium, and large. I don't like to use the cutoffs, but we can definitely see a relationship, and the correlation coefficient is in the 0.6, 0.7-ish type of range. Now, if I was to draw the line of best fit, there it is. And here's a line going through the data. Now, I'm going to add one more point. And we're going to see how much 1 point can influence the correlation coefficient. So let's see. With my mouse, I'm going to take this point and let's say drag it out here. Now, I can drag 1 point around and it's going to calculate the correlation coefficient. So I'm going to take, what do you think is going to happen to this correlation coefficient if I put one additional point in this upper right-hand corner? What do you think is going to happen? Right now it's 0.67. What's going to happen with 1 more point? Now, if I put a point up here, is it an outlier? Well, it's just definitely out of the way in the X direction and out of the way in the Y direction, but does it follow the relationship? Okay. Make your mental guess. What do you think it's going to change to? You ready? 3, 2, 1, boom. What happened to our relationship? It's magically stronger. An outlier can actually make your correlation look or come out to be a stronger value, closer to 1. And this is true if your extreme point falls in the pattern or in the line of the rest of the data. So here, I'm going to get rid of this point. If I put a point out here, it's just going to strengthen our relationship. The further away it is, it's going to strengthen the relationship if it's on that same trend in the same relationship zone as the rest of the data. Okay, so if I put my outlier out here, it strengthens the relationship, but it's still positive. It just got more positive. It's more strong in the positive direction. Now I'm going to put 1 more point. This time I'm going to put it in the upper left-hand corner. What do you think is going to happen to our correlation of 0.67? Let's see. Take your guesses. 3, 2, 1, boom. What happened? I only added 1 point and the correlation coefficient completely changed. Not only did it change from being positive to negative, it went from pretty strong to really close to 0. This is what's called a high leverage point. So let me get rid of it. I'm going to show the least squared line. This is the regression line we're going to learn about in chapter 10. When I put, if an additional observation extreme comes in, extreme or not, if it's on that relationship zone, it will strengthen the correlation. But if I go perpendicularly away from it, it's going to pull that regression line to it. So here it's pulling it here to it, and now it's pulling the back end of it. This is called an influential point. Now, there are some diagnostics that have been fancy, sophisticated things developed for finding out which points are high leverage points. But really, the best way to find out if you have a high leverage point is to plot your data. Okay, let me clear this. Okay, let's go back to our slides. So correlation is not resistant to outliers, and it's because the correlation is built, remember that nasty formula, using means and standard deviations. And means and standard deviations are highly influenced by extreme values. So if we have extreme values, it'll throw off the means and standard deviations, which will then in turn throw off the correlation. So again, always plot your data to see if it's linear, to see if you have outliers. In general, humans are not really good at looking at a plot and deciding the correlation, but you should be able to judge if it's stronger or weaker if you have two plots, and positive or negative even if you have one plot. Okay, oh, it does say what to do when you have outliers. When do outliers have more leverage? When they're not following the bivariate relationship that all the other points are kind of trending in. So, assumptions. Doing regression or a correlation analysis or calculating Pearson's correlation coefficient is, in a way, a statistical model, and it has some assumptions. The first assumption is that we have a random sample. There's no way to test this. The best you can do is get a sample that's as random and as representative of that you can get away with in the thing that you're studying in the budget and time constraints that you have. The second assumption is that our relationship is linear, straight line, not a curve, not a plateau. The only way you can really establish this is with a plot. So make a scatter plot. The third assumption is that our data, our two variables, have a bivariate normal distribution. And this one is really hard to check without making 3D plots, which are atrocious because you have to then rotate them. They're a mess. So usually we just check that each individual variable has a normal distribution, and we kind of get away with this. But this linear relationship is the most important assumption to check when you're doing correlations. Again, if you have a non-linear relationship, it's not bad, but you need to know that you're probably not going to want to use Pearson's product moment correlation. Okay, so normally, rho is normally, for the null distribution, we set up the null hypothesis that we have nothing going on, that we have a normal distribution at 0. And so we're not going to worry about a lot of the details, but the book goes into how you calculate the p-value to go with the correlation. The way that you do that is R is converted to a T statistic with this beautiful formula that someone researched the heck out of and wrote a paper on. And then they developed this beautiful table to go with the degrees of freedom, which, by the way, when you're doing a correlations p-value, the degrees of freedom is n minus 2, because we're looking at two variables. And you can look it up in this table. I'm not going to have you do any of these by hand, looking it up in the table. We're going to have R just puke out this p-value. Now, I've only once in my life ever seen the actual t-score reported with the correlation. Usually we report the correlation and its p-value, and we just skip reporting the t and the degrees of freedom. So, example. We love examples. So here's an example where I'm looking at the mood of the person, and if that correlates with their current mood correlates with their verbal memory recall. I think it's supposed to have 2 L's. So here is a tiny data set. We have 7 observations, and each person is one line. And for each person, we have their mood, as it was rated by this scale, and how many words they were able to recall that day when they did their mood. So again, we're going to start code-wise with our data set, and we're going to pipe it into core.test. And inside the core.test function, we have to do 2 things. We have to give the formula and the data set. The formula is nothing tilde wave, the name of the variables with the plus sign between them. They're on the same side because order doesn't matter. And data equals dot to pipe it from above. This little tiny bit of syntax will, by default, do the Pearson's product moment correlation. Now, this was a small data set, but in this one, the correlation came out to be 0.64, which is moderately strong correlation. But in this case, probably because it's a small data set, it is not significantly different than 0. So by default, it's doing a two-tailed test, which we almost always want to do with correlation to be conservative. So our p-value is not small. If it was small, p is small, what is it? P is low, no must go. It's not the case here. We cannot reject the null hypothesis that the correlation is 0. Okay, so things that can get you in trouble or affect the correlation. We've talked about outliers. These are not outliers in one variable or the other variable. They're outliers to the two variable partnership relationship. So we call that bivariate outliers. Heterogeneity of subsamples. If we have a data set that has a combination of two different data sets within it, this can cause a problem of calculating correlation. So if I have men and women and they are like two clumps, that can cause the correlation to have be flawed. So again, plot your data, be aware of your sample. The last one, which is the top of the slide, is restricted range. And this is the problem that we have. I kind of noted it before. If you're using a measurement scale that has a floor or a ceiling effect in your sampling population, then you can have very little variability because of a floor or ceiling effect. And then you, with no variability, you are unable to measure the true strength and relationship. We're going to watch a video in a second. I'm tired of talking. Anytime we talk about correlation, we always have to talk about spurious correlation. These are correlations that might exist not because of any true relationship, but because of other things. And it can just be random chance, a type 1 error. So here is a plot. It's a very famous plot. And on the bottom, we have years from 1999 to 2009. So a 10-year span. And we have two things plotted here. In the black line, we have how many films between 0 and 6 Nicolas Cage starred in each year. That's the black line. And then kind of mirroring it is this red line, which models the number of swimming pool drownings in that year. And it's going from 80 to 140. And if you look at those two lines, you see that they track very close together. Years when there were a lot of Nicolas Cage films, there was also a lot of drowning deaths. Is something going on? This is where we need to say this is an observational study. We did not randomize anything. We just collected data as it came in. When we do this, sometimes we'll see associations that are not causation. And we need to be careful because here we laugh, but sometimes we can fall victim to this. So we're going to watch this little video to give my voice a break.
People, I enjoy a tasty scoop of ice cream, especially Oreo blizzards. But what few people realize is how dangerous a treat ice cream has become. First, there's the issue of obesity. Second, there are higher crime rates. Third, there's the loss of life due to a rise in the number of drowning deaths. And finally, as more ice cream is sold, there's an increase in forest fires. Given these indisputable facts, I need you to support my vision of an ice cream-free world. While banning ice cream trucks from entering your neighborhood may sound far-fetched, when it comes to problem solving, a common issue is misunderstanding the difference between correlation and causation. This misunderstanding can influence our decisions, sometimes with serious consequences that ripple throughout a community. Correlation is when two things are related, but one does not cause the other. Usually this means the two are in some way related to a third factor, but not always. If you have a big enough pile of data, you can find plenty of relationships that are purely coincidental, like the strong relationship between the sale of margarine and divorce rates in the state of Maine. With the sale of ice cream, the third factor is weather. When it is hot outside, people buy more ice cream. They are more likely to go for a swim, and there is a general increase in people out and about enjoying the weather, helping improve conditions for crime to take place, as well as the dry conditions associated with forest fires. A note of caution. There's a growing trend in our digital world called data dredging. This is using analytics to sift through mountains of data, hoping to find useful relationships.
And let me stop here. Sometimes this is p-hacking. So we might measure a whole bunch of different things in a study and then do a whole bunch of correlations to try to find something that's associated with something else. And just kind of blowing off the fact we looked at 100 different pairs of variables.
Instead of a problem in search of a solution, dredging data is a solution looking to find a problem. All of what I've just discussed about correlations does not mean that finding a correlation is without value. In fact, correlations are a vital part of helping us move to the next step, the discovery of causation. Unlike correlation, causation is when you can claim that one thing causes another thing to happen. In order to make this claim, you need to be able to demonstrate an actual cause and effect relationship, preferably a strong relationship. An example most of us are familiar with is the pharmaceutical industry. In order to make the claim that a particular drug causes a certain effect, such as lowering your cholesterol or growing hair, the FDA requires companies support those claims, putting the drug through a 4-phase, 12-step process that takes approximately 12 years. This process uses control groups and clinical trials to test the drug, making sure that X causes Y and that the drug is safe. The acceptable error rate can go as high as 5% for some drugs, meaning that the clinical trials prove that there's a 95% chance the drug does what it claims. Drugs with serious health implications, such as those used to treat a heart condition, are held to an even stricter standard, requiring proof up to 99% effectiveness. Back to ice cream. What about ice cream and obesity? While it may seem like common sense that it does cause obesity, the fact is that we don't yet know the true strength of the relationship. If we look at the sale of ice cream, there's actually an inverse relationship with weight. People gain weight in the winter when sales are low and lose weight in the warm summer months when more ice cream is being consumed. This might suggest ice cream is the new diet food. Luckily, you now know to be cautious of drawing conclusions of causation from correlation. Instead, recent research on the subject has been looking at different types of sugars used in making a wide range of sweet foods. What scientists have discovered is that the hypothalamus, which is an area of the brain that regulates the human appetite, reacts differently when we consume foods with fructose instead of glucose. This has researchers speculating that eating high fructose foods, such as ice cream, may result in people not feeling full, so they continue to eat. This theory proves difficult, however, when we start considering apples and other natural fruits also contain fructose, not just ice cream and chocolate cake. As you can see, causation is quite a bit different than correlation. Finding correlations is easy, proving causation is hard. No wonder it takes 12 years just to prove that a pill causes hair to grow. The bottom line, on the news, in boardrooms and coffee shops, everywhere you go, you will hear claims that X causes Y. From politics to the weather, from the stock market to personal relationship, it is human nature to try and explain things, to create stories that make sense. Just keep in mind, as you hear a claim of what causes what, that correlation is not causation.
So we laugh about ice cream sales causing forest fires, but sometimes we, want to believe that there's a relationship so badly that we try to do similar things in our own research. So the caution is that correlation does not imply causation in observational studies. Correlation can be evidence of causation. It can help us refer strength and direction, but not form by itself unless we have a scatter plot. So in order to show that correlation implies causation, we need a randomized control trial, lots of evidence building up. We've talked about these ideas before. Some other things to know about correlation is that P-values can be very influenced by sample size. If you have a small sample size, your p-values are not going to be very helpful for correlation. And we need to interpret the size of the R value, not just the statistical significance. Now, in your book and some of the older APA manuals, it says that we should report R, and then in parentheses the degrees of freedom, which is 2 less than the sample size, then what the correlation value is, and then what the p-value is. Now, generally we say 2 numbers after the decimal for pretty much everything, except correlation and p-values. We usually report 3 numbers after the decimal. Now, for correlation, we definitely do need to put the negative sign, because a negative correlation means something very, very different than a positive correlation. But since correlation is like p-values, it's never going to have a number in front of the decimal. We do not put the 0 in front of the decimals. That's what APA says. But just last week, I had a journal article that was on a revise and resubmit, and they said they wanted the zeros in front of the decimal, even though they said they were following APA guidelines. So if you find yourself in that situation, just do what the editor wants. So here's an example of reporting in APA style. This is how I would probably write something. So it says, for the 9 students, you want to say how big your sample size was, the scores on the first quiz and the first exam were strongly and significantly correlated. Now you see, when I read it out loud, I didn't report the things that were in parentheses and the statistics at the end, but that helps that we definitely want those in there. So the summary statistics you usually want to include are the means and the standard deviations of the 2 variables separately. You'll want to put in the sample size. Now, if you've said that you had 9 students, we can infer that the degrees of freedom for the correlation was 2 less. So that would be 7. And generally, people don't put 7 in parentheses after the R, even though the older versions of APA did put it there. Again, here, this is a large correlation. It's closer to 1 than 0. And the p-value is statistically significant. It's a less than 0.05. So we can say there is a strong, positive, significant relationship. Here's a second example of reporting. And so in this first one, I just said that they were correlated and reported the R value. It would probably be better if we had enough words. So thesis and dissertation do this. Call it a Pearson product moment correlation coefficient. It's always better to give the full name, unless you have to cut words for a journal article. So a Pearson product moment correlation coefficient was computed to assess the relationship between the amount of water one consumes and the rating of skin elasticity. So the first sentence here is saying what it is we're investigating. We want to look at these 2 variables and see if there's a relationship. And to do that, we're going to calculate the correlation. And then we can say what we found. There was a positive correlation between the 2 variables with a V. And again, I'm just reporting R and P, with neither of them having a 0 in front of the decimal and both of them having 3 numbers after the decimal place. And if you're writing this as a larger document, you can include the scatter plot. So a scatter plot summarizes the results. See Figure 1. Overall, there was a strong positive correlation between water consumption and skin elasticity. Increasing in water consumption were associated with increases in ratings of skin elasticity. So again, very careful here. We're only saying that there's an association. We're not saying that if we drink more water, we will have better skin. It might be that people that are healthier are automatically drinking more water, and then have people that are healthier have more glowing skin. There might be that third confounding factor if it was an observational study. There might be something else like smoking that's a confounding factor, that people that smoke have less elastic skin, and maybe they're also less likely to drink water. We can come up with all kinds of stories. But the key is, if we're doing an observational study, we cannot jump to saying it's causation. Causation is only available in a single study if we have done randomization. So a lot of times we want to put correlations between multiple variables to get in a a document. And instead of writing sentences like that for each pair of variables, oftentimes we'll use this correlation matrix idea to display and to present multiple correlations at the same time. So this table is exactly reproduced it's from the APA 7th edition manual. And so this is a really cool kind of table because we have 7 variables and they're listed out. And for each variable, we have the number of observations we have and the mean and standard deviation. So this is a descriptive table of all these variables as far as having the mean and standard deviations, as well as having the correlations. Now, there are 7 variables here. And so down the side, we've listed the names of all those variables. And if there were any abbreviations, you would want to include those as notes at the bottom of the table. And then across the top, we've just numbered them 1 through 7 to match the 1 through 7 down the side. On the diagonals, APA 7th now says on the diagonal, instead of putting a 1, because every variable is correlated with itself perfectly, you should put a dash down the diagonal and leave the upper triangle blank. And then if you are usually having a lot of correlations, we usually would only put the correlation R numbers. This is shown to 2 decimal places. You could go 3. And instead of trying to jam all the p-values in there, often we will just use asterisks, either 1 or 2 or 3, to display what correlations are significant. And you can even bold those values that are significant as well to draw more attention to them. So this is manual, page 215 has this about correlation tables. Okay, so let's get into using R. I know we're coming up on the hour. I'm going to try to get this through quick, but completely. So this is the cancer data set that we've used multiple times. We have some variables in here. Here we have the total oral condition at intake. Remember, these are cancer patients that their treatment gives them cankers in the oral regions, in their mouth and in their throat. So they're measuring using some scale the condition on an index for how bad the sores are in their mouth. And so they have this at baseline, at intake, and at week 2. Now, we have randomized to treatment and control. We're going to ignore that for a second. So, again, we saw this briefly before. We're going to take the name of the data set, and then we're going to pipe it into the core.test, which is a function in base R, so we don't have to say what package it's in. Then we're going to give the formula. For correlation, the formula always is nothing, tilde wave, and then the 2 variable names added together. Same side because there's no X and Y. They're just 2 variables correlated bidirectionally with each other. And then data equals dot. This syntax up here first does the exact same thing as the syntax below it, where we've specified we want a 2-sided test. Because by default, core.test does a Pearson correlation coefficient for a 2-sided test, and it will give us a 95% confidence interval. It does all those things by default. So here is my output. Got a lot of things going on here. At the top, it tells us what we're doing. It's a Pearson product moment correlation coefficient. And it tells us the name of the 2 variables that we're correlating in our data set. Again, only 2 variables at a time in the core.test function. At the very bottom, it tells us in the sample, our correlation was observed to be 0.31. So 0.31 is positive. It's mildly strong. That's a mild correlation of 0.31. In the middle, we are given a 95% confidence interval. Ooh, check that confidence interval. It goes from a negative number to a positive number. If our confidence interval goes from a negative number to a positive number, it includes 0. And 0 is our null hypothesis of nothing going on, no association. So if we check this p-value, we see nothing's going on, no evidence of an association between oral condition at intake and oral condition 2 weeks in. And degrees of freedom are 23. The sample size here is 25. So if we were going to report this, I would say that oral condition after 2 weeks or at 2 weeks into the program was not significantly correlated with condition at intake. And then I should report R. I can get away without the degrees of freedom if I've stated the sample size somewhere else. We definitely want the p-value. R and P, we probably want to give 3 decimal places, no 0 in front of the decimal. And it's always a good idea to give effect size measures, and that could include giving the confidence intervals. And when it's negative and positive have implications and correlations, so you want to include those negative and positive signs. So by default, core.test is doing a two-sided alternative. If you look into the output, it tells you that the alternative hypothesis is that the true correlation does not equal. So not equal is a two-sided. It allows it to be bigger or less than 0. If it's less than 0, that's negative. If it's bigger than 0, it's positive. So there is a way to do a one-tailed test for correlation. If you think that things are positively correlated or negatively correlated, you can customize your core.test to only look at the one-tailed alternative. And the way you do that is you add in either alternative equals less, and this is for if you want to test if you have a negative correlation, or alternative equals greater if you want to test if there's only a positive association. Now, these will give you one-sided p-values, but they have kind of a drawback. When you do say that you want a one-sided test, check out what happens with your confidence interval. The less one, the confidence interval will always be -1 to a number. And if you say greater, it's always going to have something going up to +1. When you do a one-sided test, you should not look at the confidence interval. So if you want to do a one-tailed test and a confidence interval, you would have to do the less than or greater than to get the one-tailed test. And you would also have to do the basic one to get a meaningful confidence interval, because confidence intervals always need to be symmetric and have both directions, not have one side of the confidence interval maxing out at -1 or +1. So that's just a little catch when you're doing one-sided tests for correlation. So making those correlation matrices with multiple variables, instead of doing a core.test for each pair, you can do table C out of furniture. So we're going to, again, start with our data set, pipe it into the furniture table C for correlation, and then in the parentheses, list out all the variables in our data set we want to see the correlation between. Now, by default, there can be something that happens when you have missing values. So in this data set, everyone has a value at intake at 2 weeks and 4 weeks, but at 6 weeks, some people dropped out of the study, and so they have a missing value at 6 weeks. So we've seen this option in several things. NA.RM equals true. That will not, the NA is the missing values, RM is removed. So this will take the missing values and remove them. This is doing what's called listwise deletion in a correlation matrix. So in this original way, when I did the correlation matrix, you can see this bottom line has a bunch of NAs because it can't calculate a correlation where one of the variables has missing values. And since week 6 is the only variable that had people missing, we can't do any correlations between a pair of variables where week 6 is one of those two variables. So if we use the default, it's going to have a problem and have all these NAs produced. So by including this NA.RM equals true option, we'll do listwise deletion, and now we will get all of our correlations. To do this, though, your sample size will be reduced to just the people in the sample that have complete data. So you want to be careful about knowing which variables have missing values before you just willy-nilly throw variables into a correlation matrix. Okay, so scatter plots with a line. So there's a couple things to do with the scatter plots. So scatter plots we're going to use ggplot like we've done other things. So you're going to start with the name of your data set, and then you're going to pipe it into ggplot. Now for the aesthetics, you have to give it which variable is the x-axis on the bottom and which variable you want on the y-axis up the side. Now for correlation, it does not matter. When we get to regression, it will matter which one's on the x-axis and which one's on the y-axis. But for computing correlation, your scatter plot can go either way. But you have to say which one you want. So you say x equals the name of the variable you want on the x-axis, and y equals the variable you want on the y-axis. And then once we started ggplot, we use the plus to add layers. So we're going to add geom point. And this is going to make all the points, one for each person. Now that makes our scatter plot, but we often want to add this smoothing line. This is the line of best fit, and it has some confidence bands around it to get a picture of what the relationship is. And we're going to do more with this smoother line in the next chapter. But let's go over it. Geom smooth, we want to say method equals LM. LM means linear model. So this will get the line of best fit. Now, here I've used the geom point to get us the dots and the geom smooth to get the line of best fit. And LM means linear model. If you leave that part off, it will do a moving average smoother like we've seen on all these COVID histograms lately. So again, geom point will make a point for each observation. Now, in this case, we have some granular data. The values were whole numbers, 4, 5, 6, 7, 8, 9, 10, and then a 12 value. So they're whole numbers on both the X variable and the Y variable. And so what happens here, if we have two people that had the same X number and the same Y number, then they would have dots that are on top of each other. We call this overplotting. And on this scatter plot with geom point, you can't see if there's any overplotting. So there is a slight variation on a scatter plot where instead of saying geom point, you say geom count. And that count word makes that these points get bigger if there is overplotting. So you can think of it as we're dropping points down like water droplets, and if two drops fall on the same spot, it spreads out. So we can see that there are a lot of people at intake that had a value of 6. So we have these extra points that are built up here. And so if you have a very granular scale or a very large data set, using geom count can help give you a more fully fleshed picture than just using geom count. Okay, so there's a way we can get the pictures to go along with our correlations. And we're going to leave it there. We'll answer questions in class, and the next recording will be on linear regression.